Welcome back to Mr. Hassan's Maths channel. I'm now answering a question from one of the GCE UK A-level papers, 9MA0, paper 2. This is from October 2020, which is actually June 2020, which was cancelled because of COVID. And here we have a question about the modulus function. So in this question, we're told a figure 2 shows a sketch of the graph with the equation y equals 2 times the modulus of x plus 4 minus 5. And so the vertex of this graph is at the point P as shown in figure 2. It says find the coordinates of P. Now by far the easiest way of finding the coordinates of the vertex of a modulus function when it's like this type of linear type where you have straight line parts is very similar to finding the vertex of a quadratic function. All right, because in a quadratic function, supposing this was 2 times x plus 4 squared minus 5. Okay, we would say that the vertex is minus 4 minus 5 if we saw something like this. Because the reason why we say that is because this thing is always going to be positive. It's always going to be squared. So whatever value of x you put in here, this thing will always end up being positive. So the lowest this whole expression can be, okay, is negative 5. You're always taking a 5 away from whatever's here. You're always taking 5 away from whatever's here. And the lowest that this can become is 0 when x is minus 4. When x is minus 4, this whole thing becomes 0. So the lowest the whole of this expression can become is negative 5. Because the lowest that this can become is 0 when x is negative 4. So the vertex is when x is negative 4, y is negative 5. So it's always the same number in here except with the opposite sign, and whatever's left outside is the y coordinate. So this is the x coordinate with the opposite sign, whatever makes this bracket 0 basically, and whatever's left outside when this whole thing becomes 0, that's the y coordinate of the vertex. Now the modulus function is almost the same in terms of that concept, that whatever goes inside this modulus sign comes out as positive. So in this case, the same kind of thing applies. This whole thing, whatever value of x goes in here, this thing is going to be positive, right? So you'll have 2 times something positive minus 5. So you're always taking away 5 from something, all right? Now the lowest this thing can become, again, is 0. What makes this thing 0? When x equals negative 4. When x equals negative 4, this whole thing becomes 0, and you're left with minus 5. So when x equals minus 4, minus 5 is the lowest this can ever be. So the coordinates of the vertex are minus 4, minus 5. As simple as that. So it's like completing the square. You just look at the coordinates, you look at the modulus function, and whatever's inside this bracket, you can put here minus 4, and then whatever's outside, minus 5. So when x equals minus 4 and y equals minus 5, that is the vertex. Those are the coordinates of this vertex here. That's by far the easiest way of finding the coordinates of the vertex. There are other ways you can do it. Okay, you can find, for example, the 2 places where this hits the x-axis, and then you can find halfway between them for the x-coordinate, and then substitute that into the into the equation for the y-coordinate. You could do that, but this is by far the easiest method. If you can see that, then that's, really makes life a lot easier for you. Okay, there's lots of different ways to find the vertex, but I find this is the easiest way. In fact, some of my older videos I didn't actually used to explain this way, but I find this way is way easier and more efficient to find the coordinates of the vertex. Okay, now to solve part B, it says solve the equation 3x plus 40 equals 2 times the modulus of x plus 4 minus 5. So basically this is y equals the 2 times the modulus of x plus 4 minus 5 is what we have sketched, and y equals 3x plus 40 is a line that we want to know where these two intersect, basically. That's what this means. Where does this line intersect that line? That's where they intersect will be the x values of the solutions of this equation. Okay? Solution or solutions. So basically what I'm going to do here, there's 2 ways of us going about this. We can solve this purely algebraically and then check our answers back into the original equation to see which one of the answers satisfy the equations. If one of them, both of them, none of them, however, we will, the answers we get, we must check with the modulus function. You always must check to see that they answer, because sometimes that they are correct. So because sometimes you get false solutions, and you'll see why when I show you graphically. So I'm going to show you graphically how to solve this equation, because I find that helps you understand what's going on. So I'm going to show you how to do that first. So basically, we have this, we get y equals 3x plus 40, and this equation here we have to solve. Okay, so now y equals 2x plus 4 minus 5 has a positive argument and a negative argument. The positive argument is when you treat the modular sign like a bracket without any other change. So it's like 2 times x, which is 2x. So you have y equals 2x. 2 times 4, which is 8. 8 minus 5 is 3. So 2x plus 3. So in this case, this line is y equals 2x plus 3. That's a positive argument of this, modulus function. So that means it crosses the y-axis at 3. It crosses the x-axis over here, which is going to be minus 3 divided by 2, which is negative 1.5. And the negative argument of this graph is when you treat, like when you change this, or you change the sign of everything inside the modulus sign. So it's like you put minus 2 outside instead of 2. So it's minus 2 times x, which is like y equals minus 2x, and minus 2 times 4, which is minus 8, minus 8 minus 5, which is minus 13. It's like I've changed this for a minus 2, and that became minus 2x, minus 8, and then minus 8 minus 5 is minus 13. So this graph is, this is the negative argument of the graph, and it goes through, we can see negative 13, and when y is 0, you will have negative 13 over 2, which is negative 7.5. That's where it's going to cross the y-axis, the x-axis, sorry. Okay, so that's the negative argument of the graph. That's the positive argument of the graph. Now y equals 3x plus 40. It's going to have a positive gradient. So it's going to be going like this. It's going to be more steep than this. It's going to be steeper than this graph. It's going to cross the y-axis at 40, very high up, somewhere really high up, and it's going to cross the x-axis at minus 40 over 3, which is more than minus 12. So it's going to be quite far down here. So it's going to be steeper. It's going to be steeper than this graph because the gradient is greater. So you have y equals 3x plus 40. It will be something like this. It's going to cross way further up there, right? So we can see here that there's only one intersection possible here. This is the only place they're going to intersect, somewhere over there. There's no way they'll intersect anywhere else because this line is going to be going, less steep. This is more steep. They'll never get closer together, right? So this will be only one solution to this equation. And we can see visually that solution is going to be where this and this will intersect. For this and this, there will be no intersection. There might be algebraically, but in the graph, there's no intersection because algebraically, you will get a solution if you do it. And that will be where the continuation of this line, which doesn't actually really exist, continues on and meets with this line. So it's going to be something x equals negative, further negative than this. It's going to be where this continues on and meets that line. That will be a solution algebraically to these two together, but that won't be actually a solution that satisfies our equation. Okay, our equation with the modulus, because that modulus doesn't go that far, right? This stops over here. Goes back up again. So this is the only solution. So we can see visually what to choose to find the solution, and we don't really have to, find the other, solve two different equations. We can just see visually it's these two that we have to solve, and that will give us a solution, and that will be the only solution. So we got y equals minus 2x minus 13. So when 3x plus 40 is equal to minus 2x minus 13. Okay, so that's going to give you 3x plus 2x equals minus 13 minus 40. So you have 5x equals minus 53. So x equals minus 53 over 5, which is minus 10.6. Minus 10 and 3/5, which is minus 10.6. So x equals minus 10.6 is our only solution. And that's it. And we've got the answer. We don't have to check anything because we can see that's the solution. Okay. If you want to check in case we made a silly mistake that, it satisfies the equation, we can. But in terms of checking to see if, is this a false solution? No, we don't need to do that. However, if we did this purely algebraically, okay, without taking care of, looking to see where the intersections would be, then, we would have basically considered it in this way. We would have taken the positive and negative argument. And what you would have done, probably, you would have started off with this. You'd have started off with 2 times the modulus of x plus 4 minus 5 equals 3x plus 40. And then you'd say, if you take the negative argument, it would be minus 2x. In fact, no, that's a positive argument we want. That's a negative argument that gave us a solution. So the positive argument, you see, the positive argument is the one which doesn't give a solution with this. So if you would have just treated it like this, you'd have 2 times x plus 4 is equal to 3x minus or plus 45, adding 5 to both sides. So you have x plus 4, the modulus of that is equal to 3x plus 45 over 2. And then we'd say, okay, the positive argument of this is when x plus 4 equals 3x plus 45 over 2. And the negative argument would be x plus 4 equals negative that. That would have led us to that solution when we said x plus 4 equals negative of this. But the positive one is going to be basically, if we solve this, let's just get rid of the fraction. So we have x plus 4, that gives you 2x plus 8 equals 3x plus 45. So we end up with 2x, well, you have 8 minus 45, which is minus 37 equals 3x minus 2x, which is x. So x equals minus 37. That is the solution, which is a false solution. I know it's false because graphically we can see that it's false. Okay, but supposing you hadn't done that, supposing like we took the positive argument and got this answer, we took the negative at this point, we took the negative argument, we would have said x plus 4 equals minus 3x minus 45 over 2, and then we would have solved it and got these two solutions. So when we check these solutions, if we do it algebraically, I haven't got the graph, we would have to check both solutions. So when we check x equals minus 10.6, I'm going to put, I have my left-hand side, I have my right-hand side. The left-hand side is going to be 3 times minus 10.6 plus 40. And the right-hand side will be 2 times minus 10.6 plus 4 minus 5. And I'll check what that gives me. So I have 3 times negative 10.6 plus 40. That gives me 41 over 5, which is 8.2. And this will give me, I'll have minus 10.6 plus 4, but because it's inside the modulus sign, that's going to become positive. When you modulus of minus 33 over 4 is 33 over 5, sorry, times 2, and then take away 5. That gives me, oops, what did I do here? What did I do there? Sorry about that. Let me just do that again. I think I did something wrong here. So you have negative 10.6 plus 4. Okay, that's going to become positive. And then I have to multiply that by 2. And then I have to take away 5. It gives me 8.2 here. I think I posted something wrong. So we know they're equal. So we know that this is a correct solution. So this is a correct solution. And when I try x equals negative 37, I have 3 times negative 37 plus 40 on this side. I have 2 times the modulus of negative 37 plus 4 minus 5. Let's see what that does to our equation. So we have 3 times negative 37 plus 40. That gives me negative 71 on this side. And then I have, let's do this. So negative 37 plus 4, which is, I think, negative 33. That becomes positive. Oops. What am I doing? So negative 33, it's going to be positive. So we have 33 times 2 and minus 5. Okay. That gives us 61. So we can see that they're not the same. They're not the same. So therefore, this is a false solution, as we can see from our diagram. Okay, if you continue this line along, and this line, they're going to meet somewhere over there. As we can see, if we continue this along, they would meet somewhere further down over here. Okay, continue this and continue that. They're going to meet somewhere over here, which they don't actually really meet, because this line, which I've drawn dotted, doesn't actually continue because it's a modulus function. But algebraically, they will meet somewhere over here. Okay, and that would be minus 37. And that's why this does not satisfy our modulus equation. So if you did this purely algebraically, you would get two solutions, you would check them both in the equation, and you would only choose the one that satisfies the equation. But if you do it graphically, if you just draw a little sketch here, you'll see that there's only one solution, that's where this meets that. You can solve it and get the answer without having to do these checks. All right, so there's the answer to part B. I've spent a long time explaining these, but I want you to have a bigger picture, or a clearer picture of what's going on, not just algebraically, also visually and graphically what's going on, because some people understand things better visually, some people understand things better algebraically. Sometimes when you combine them together, it gives you a way better understanding. So please bear with me, those of you who just looking. As I said, I'm not here to be a talking mark scheme. I'm here to try to explain to people so they get a deeper understanding of the maths behind all of this. So the last part of this question is as follows in the next section. So it says a line L has equation y equals ax, where a is a constant. So y equals ax, of course, this passes through the origin, goes through the origin. Okay, because it's plus c, c is 0, right? Y equals ax. So a is basically a is the gradient. A is like the gradient, you could say m. Okay, given that the line L intersects this equation, this modulus function, it's the same as we had before, at least once. At least once means once or more than once. At least once. Okay, not only once, at least once. So it's important to know the difference between these wordings. So that means you can intersect it one time, or it can intersect it two times. Find the range. Well, it can't even two or more times, but we can't. Of course, I don't think it will ever. Two straight lines can never intersect, more than once like this. If one of them is a modulus, I think it'd only be twice it could intersect. So find the range of possible values of a, writing your answer in set notation. So they want us to use set notation here. That's one thing, right? So at least once, okay, and the fact it goes to the origin. And the gradient of the line is a. So a is a gradient. So let's just do a bit of investigation here. And we've got a straight line. Now this straight line, I'll make it a bit thinner. So, okay, so this line we know passes through the origin for sure. It passes through the origin. Okay, so it has to cut at least once. Now, if the line has a gradient which is like more than the gradient, which is more than this. So this is one of the limits where we'll intersect. Okay, I mean if it's got a gradient which is shallow, it's going to cut it in two places like this, two places like this. Okay, but there's a limit over here where that vertex is, which connect the line that connects the vertex to the origin. That line over there, okay, that's going to be a limit to where it will stop intersecting, because here it touches it at the tip. When it goes, when the gradient is less, when the value of a is less, it's shallower, it's a positive gradient but less, it's going to cut it twice, okay, and it'll continue cutting it, and we'll see the limits for that in a minute. So basically, if the gradient is greater than this value here, okay, if the gradient is greater than this value here, then it won't intersect at all. Okay, it will be like this. Okay, it's not going to intersect because it's going to miss that, right? So we need to know what that gradient is. That's the limit here of one of the gradients. So I know that the point P, we worked out the point P has coordinates, as we can see, -4. Sorry about that, get the proper pen back. So you got -4 and -5. As we said, that's how we, -4, -5, that's the vertex. And this is the origin where this line passes through. We know 2 points that the line passes through. We can find the value of its gradient. Okay, it passes through the origin, which is 0, 0. So we can say the gradient of the line here at this point is going to be, you can say 0 -5 over 0 -4. 0 minus -5. Okay, you can say 0 minus -5 over 0 minus -4, which is going to give you 5 over 4, which is 1.25. So That's one of the limits. When it's equal to 1.25, that's one limit. Okay. Now, what's the other limit? Okay, we can see it won't intersect, it won't intersect, it won't intersect. Okay, now, when this gradient of this line is exactly 2, these will never intersect as well. These will never intersect. But if it's more than 2, eventually this line will intersect with that line, because if you continue this on, yeah, as long as this gradient is more than 2, if the gradient of this line is more than 2, it's going to eventually intersect. Even if it's 2.0001, eventually somewhere they're going to intersect one more time. Okay, so the limits of them intersecting at least once are when this gradient here is more than 2. And here it's when the gradient of this is less than or equal to 1.25. Okay, so these are the two values, because when the gradient of this is equal to 1.25 or more than 1.25, okay, at this point here, that's where the gradient is equal to 1.25. If the gradient becomes more than that, becomes steeper than that, then it won't intersect at all. But if it's less than that, the gradient is less than 1.25, it's going to intersect. It's going to keep intersecting twice. At least once means twice is fine. Even if it's a really small gradient. And even if the gradient becomes negative, when the gradient is negative, even when the gradient is 0, they'll still intersect. Okay, more than once, at least once. And when the gradient is negative, you can see the gradient is negative, these lines will intersect twice, at least once. They'll continue intersecting. Even when this gradient is over here, at least once, even if this is -2, even when this is -2, okay, it's at least once intersecting over here. Okay, so it can go all the way around. Okay, but where it will stop is going to be at that point where we said when this becomes like that. Okay, that's where it stops intersecting. Okay, when the gradient becomes when the gradient becomes more than 1.25, they stop. So the range of possible values of A. So this is the gradient. So we'll say A has to be less than or equal to 1.25 and A has to be greater than 2. Now in set notation, what we can say here is A is such that A is less than 1.25 union with, because these are like, not intersecting. A is such that, we should use the squiggly brackets really. A is such that A is greater than 2. And we can say A is a member of the real numbers, but that's fine. That's fine. That's in set notation using union, because these are like not overlapping or anything. So it's when this is that, or when A is less than 1.25, or when A is greater than 2. Those are the situations where there will be at least one intersection. Okay, so I hope that was clear. All right, you have to just visualize what this, how this line will intersect as it goes along, and you can see that this is going to be the limit of one of the points where it will intersect. Okay, if the gradient of the line increases more than 1.25, it's going to not intersect until it reaches 2. So it has to be less than 1.25, and then it has to be greater than 2. When it's greater than 2, they're going to intersect again at least once up here somewhere. Okay, somewhere up here they'll intersect again. So those are the two. So they asked us to use A. I used A in the end. That's how we should use it, because they gave us A as a gradient there. So there's the answer to question number 11. I hope that was clear. This question, as I said, is from the October 2020 UK A levels, but it's very much relevant to P3 in the international A level. So thank you for watching. Other questions from this particular paper will be found in the playlist that will appear in this region over here. Other questions from the topic of the modulus function and graphs and functions of P3 will be found in this playlist over here. You can subscribe to my channel by clicking on this link, and you can watch the video, the link for which will appear over here, which tells you how to use my channel efficiently. Thank you for watching, and see you soon.